Day 15. 2, 1. Go. Beacon exclusion zone. You feel the ground rumble again as the distress signal leads you to a large network of subterranean tunnels. You don't have time to search them all, but you don't need to. Your pack contains a set of deployable sensors that you imagine were originally built to locate lost elves. The sensors aren't very powerful, but that is okay. Your handheld device indicates that you're close enough to the source of the distress signal to use them. You pull the emergency sensor system out of your pack, hit the big button on the top, and the sensors zoom off towards the tunnels. Once the sensor finds a spot it thinks will give it a good reading, it attaches itself to a hard surface and begins monitoring for the nearest signal source beacon. Sensors and beacons always exist at integer coordinates. Each sensor knows its own position and can determine the position of a beacon precisely. However, sensors can only lock onto the one beacon closest to the sensor, as measured by the Manhattan distance. There is never a tie where two beacons are the same distance to a sensor. Okay. It doesn't take long for the sensors to report back their positions and closest beacons, your puzzle input. For example, boop, 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 boop. Okay, so obviously we're going to have some that hit the same beacon over and over. Maybe the question is how many beacons? So consider the sensor at 218. The closest beacon to it is minus 215. For the sensor at 916, the closest beacon is 1016. Drawing sensors as S and beacons as B, the above arrangement of sensors and beacons looks something like this. Okay. This isn't necessarily a comprehensive map of all beacons in the area though, because each sensor only identifies its closest beacon. If a sensor detects a beacon, you know there are no other beacons that close or closer to that sensor. There could still be beacons that just happen to not be the closest beacon to any sensor. Consider the sensor at 87. Okay. This sensor's closest beacon is at 210. Okay. And so you may know that there are no beacons that close or closer in any of the positions marked with a hash. None of the detected beacons seem to be producing the distress signal, so you'll need to work out where the distress beacon is by working out where it isn't. For now, keep things simple by counting the positions where a beacon cannot possibly be along just a single row. So suppose you have an arrangement of beacons and sensors like in the example above, and just in the row where y equals 10, you'd like to count the number of positions a beacon cannot possibly exist. The coverage from all sensors near that row looks like this. Okay. In this example, in the row y equals 10, there are 26 positions where a beacon cannot be present. Consult the report from the sensors you just deployed. In the row where y equals 200,000, how many positions cannot contain a beacon? That's a big number of rows. Oh, so that's 2 million. That's a lot of rows. Okay. All right, today's is a little bit too long to cut down to a reasonable sized video again, so I'm just going to walk through the answer again. We're going to start off with two data classes, one for sensor, one for beacon. They're just going to hold the coordinates for those items and for the sensor, the maximum distance that I can see. We need to be able to find the max distance, so I added a helper function that does that, takes a sensor and a beacon. And since we're using Manhattan distances, which are like up, down, left, right only, then it makes it a lot easier. So if you think about it like from a chessboard, for example, if you wanted to move one space diagonally, a rook would have to move up one and then over one, as opposed to a king, which would just move in one spot. So to find that max distance then makes it really easy because we only care about the absolute value of the x difference and the y difference. And then we're just going to add those two together and save it back as our max distance. Easy enough. And then I also added a helper function for spots covered. So that's going to take a sensor and a row. And for that row, it's going to find out how many of those spots it can see and give us a range back. So like it's going to return basically a pair of long, long, which is going to tell us the furthest left and the furthest right. The way this works is because since again our max distance has to be Manhattan distance, we can just take the y difference between the two pieces and we know how far X we can go and how far X we can go in the other direction. And then once we add those together, that's our range, pass it back up, we're done. So the next part is to bring in all of our information. So for each line, I just created a regex, which I should pull that out. Not a problem, I'll clean this code up in the GitHub down below. And then for each of those values, which is going to match like each of these here, then we're going to add it to our list of sensors for the first two and add it to our list of beacons for the second two. Well, I say list, I used a list originally. It bit me because some of the beacons are repeated, so I changed that to a set. And then we're going to also update the distance for that sensor as well with the last beacon. Then to find our how many things that we cover in a row. Basically what I did is I added a list of ranges, which is, we're going to go through and call that spots covered function for every sensor. And as long as it covers that row, we add it to our list of ranges. Now, a lot of these ranges overlap, and so then we have to go through and figure out how the overlapping stuff works. I put it in just to help me kind of figure this out. Basically, there's 4 different ways they can overlap. So they can overlap on this edge, you know, or be completely contained. And so what I'm going to do is go through for every pair. I'm going to look to see if A is less than D and B is greater than C. And if so, I'm going to remove both ranges, and then I'm going to add a new combined range, which is going to be the leftmost value, which would be A here, C here, and all the way to the rightmost value, which would be like D or B. And then basically if I find one of those, I break and I do the whole loop again. I keep doing that until I don't find any more that overlap. At which point, the only thing that we need to do is basically sum up our ranges, which for the most part are usually just going to be 1, which we'll get to in a second. And that's going to take our, basically our max value minus our min value plus 1 because it covers the ends. And then I'm going to subtract how many beacons are on a row. I said earlier, do it in a set, so it's easy to find out how many are there just by doing a filter. So that's it for part 1. That's the right answer. You are 1 gold star closer. Oh my god. Okay, continue part 2. Your handheld device indicates that the distress signal is coming from a beacon nearby. The distress beacon is not detected by any sensor, but the distress beacon must have X and Y coordinates each no lower than 0 and no larger than 4 million. To isolate the distress beacon signal, you need to determine its tuning frequency, which can be found by multiplying its X coordinate by 4 million and then adding the Y coordinate. In the example above, the search space is smaller. Instead, the X and Y coordinates can each be at most 20. With this reduced search area, there is only a single position that could have a beacon. X equals 14, Y equals 11. The tuning frequency is some large number. Okay. Find the only possible position for the distress beacon and what is its tuning frequency. Great. So for part 2, since we already have the ability to reduce a single row to a set of ranges, basically I just did that for 0 until max coordinate, which you pass in. It's probably not the most efficient path. There's probably some trickery you can do to make that runtime a little bit slower, but it still ran about 4 seconds or less, so it was perfectly acceptable for this, and obviously way easier to code. And so then I basically copy and paste everything from the first one. It does all the same information. The only difference is if the ranges happens to be greater than 1, then we're going to return. Since we know that there's a singular value that fits, basically we're going to go through the first row. It's going to reduce, 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 reduce. There's only 1 range. Great. We go to the second row, reduce, reduce, reduce. There's only 1 range. Great. And we do that over and over. And when we find a row that has 2 ranges, then we know that there's 1 spot in between them that must be the answer. And so whichever one is the lowest, take the end of that, add 1, multiply it out, and that's our answer. So pretty quick, easy thing for that. Again, maybe not the most efficient. I'm sure there's some trickery that some people have done that it's going to be more clever than that. But as far as programming, took like 2 minutes. So, okay, now we get to see how long this takes to run. Oh, that wasn't so bad. Okay. And then let's head back here. Right answer. You completed day 15. Okay. All right. Cool. Played day 15. Again, all the cleaned up code and everything will be in the GitHub. And other than that, see you tomorrow.